So today we're going to talk about applied digital intelligence, about the program as well as the concept itself, what it entails and what you can expect to study and what kind of project, what kind of analytical framework you can expect to see. Okay. Now, if you notice in this, let's make this presentation, right? Just a second. It's a presentation screen. How do I do it? Oh, sorry, this is blocking it. There. Okay. If you'll notice, I put a little arrow here. So it's the title of the talk, of course, is Applied Digital Intelligence. But the way I'm going to cover it is to go from intelligence, then digital, then applied. You'll see what I mean in a minute. Okay. Right. So first of all, I like to throw this schematic out. I'm trying to hide this. Is this thing blocking your view? Is it? Yeah. It's a little bit hard, but anyway. So there's yeah. Let's put it here. Okay. There are actually 4 concepts that you hear thrown about quite a bit in the popular media and in conference or even academic programs. So the way I like to start off my talk is to give you these 4 things and how they relate to each other. So there's a little bit of a Venn diagram going on, okay? But the area is very transdisciplinary in itself. So it's not a hard and fast distinction, okay? But it's good to think of it in these 4 terms. One is AI or artificial intelligence. One is ML, machine learning. One is quantitative models or quantitative modeling, and one is DA or data analytics. The way I like to preface this is to say that artificial intelligence, and we'll go into a more in-depth discussion of what that entails. But let's say artificial intelligence, a little bit about studying, what makes a machine as smart as human beings or something like that. In a way, the study of artificial intelligence or how to replicate human intelligence in artificial form kind of like motivates the study of machine learning. In other words, if you're going to get a machine to be as intelligent as human beings, and human beings are not born intelligent, we are intelligent by virtue of learning, which is why you are getting your education. Likewise, there has to be an analogous process happening within digital or computational domain. So just as human acquire intelligence through learning, so does machine. So in a way, you can say that artificial intelligence, if it's the aim, okay, it has to be achieved by some kind of mechanical learning or machine learning. So artificial intelligence, in a way, motivates machine learning. And then machine learning then has gone on to become a huge field on its own. Why is that? Because once you have machine learning, the machine is capable of representing reality. Now, representing reality is what analysts do. It's called modeling. So in a way, humans have been doing quantitative modeling. That's what mathematics is, right? We're modeling y as a function of x. It's a linear function of x. It's a quadratic function of x. It's a quintic function and so forth. So human beings, mathematicians, have been modeling quantitatively relationship in nature. So now if the machine can learn the relationship, you can think of using machine learning to build quantitative models. Right? So that's the next stage of evolution. But quantitative models, the reason, once you have quantitative models, it's sort of like a relationship between X and Y, right? X and Y. But of course, we are now a mass, not with abstract X, abstract Y. We are a mass with real data. So huge amount of real X, huge amount of real Y. But we have no way of relating those data. So in a way, the quantitative models that relate abstract X with abstract Y become something that drives the modern analytics. Okay, so you have huge X, a whole bunch of X, a whole bunch of Y, we have no relationship. And we have quantitative models that relate Y mathematically, quantitatively to X. You apply it. So basically, that's what I mean by saying that quantitative models drives analytics. Once it drives analytics, it turns out that with the power of modern computing, okay, and populated with the world populated by a huge amount of data, then a machine can learn so much to the point where a machine can identify cats and dogs on the internet just as good as a human being. So in a way, it comes back in a loop. So data analytics and the success of the ability to deal with a large, huge amount of data we have today turns out to validate the original aspiration, which is artificial intelligence. So we kind of like go in circle. So look at this picture as sort of like AI to machine learning to quantitative models to data analytics and back to artificial intelligence. Having said that, it's also a real Venn diagram in the sense that you can identify different areas. So there are like light blue colors. So those are sort of like hardcore machine learning or hardcore artificial intelligence, data analytics, quantitative models. And then there are overlapping areas. Okay, so darker blue would be like, overlapping in two areas. And a lot of time you get into this sweet spot where you're actually using everything. And a lot of my project is actually happening in the yellow thing in the middle. So it's sort of like an amalgam of all this approach. And that's the virtue of cross or trans or multidisciplinary study. And that's the essence of BAScii, okay? But having said that, again, this is still very closely related idea. With BAScii, you may have something like this, and then another specialization in, let's say, bioinformatics or cellular biology, all right? And then you have that sort of like a exchanging idea and approach, and this is a solution to that problem motivates this solution methodology and so forth. Okay, so that's a good slide to start, and for good reason. This is the longest slide I'm spending time on. Okay, the rest I actually have, I think, about 70 slides. A lot of it are just sort of like screenshot of applications, so we'll go over them quite briefly. Right. So this is kind of my glossary. I'll actually have this available to any of you who like a deeper meaning of artificial intelligence, business intelligence, computational intelligence, enterprise machine intelligence, machine learning, deep learning, quantitative models, analytics, what a quantitative analyst does, what's an enterprise analytics, what's big data, what's data mining, data science, and so forth, right? What's Internet of Things, network economy, digital economy, right? What I like to do is show you first this picture. This is kind of like a schematics of how I design BAScii's applied digital intelligence. Okay, so we'll go over this, and in a way, I kind of separate the knowledge stream into 3 tracks, and then I separate them further, and then these are sort of like the courses that would be designed around it. Okay, so this is I can start with this, but I think it's better for me to come back to this and go through them one by one so that you can get an idea of what it would be like to study applied digital intelligence. But the first thing is to get the concept going. So let's start with intelligence. Actually, you know what? Intelligence does have very broad meaning, but it's good to think of types of meaning. There are actually 3 different kind of meanings, okay? And today I'm going to talk about what's called computational intelligence. Okay, so when you talk about intelligence, in this sense, the broadest sense, we talk about computational intelligence. Okay, but let's go to the 3 meanings that I was alluding to. There are 3 meanings. Let me hide this. Yeah, I think if I hide here, it's gonna not be obscure. Okay. There are actually 3 meanings of non-human intelligence. Okay, in other words, if you talk about AI, yeah, you throw the word AI for anything that's non-human, but in fact there are actually 3 meanings of non-human intelligence. Okay, originally, okay, this is originally, by the way, AI means only one thing. Okay, AI means only one thing: getting the machine to artificially replicate or mimics human cognitive ability. So in other words, intelligence here is a synonym for human. Okay, so human beings are intelligent animals. If you get a machine to perform logical cognitive function like human beings, but do it in an artificial creation like a computer, like a digital computer, that's called artificial intelligence. So the idea is human-like. In fact, you can build a perfect artificial intelligence model that, is completely successful 100% in replicating a 3-year-old. Okay, let's say if you can do that. Now, would you and I consider asking a 3-year-old for advice? No, we won't, right? We won't ask 3-year-old advice because we don't think of 3-year-old as giving us intelligent answer, right? But in this case, intelligence means human being. So if the computer can mimic a 3-year-old, it's a perfect AI machine. That's the meaning of intelligence, okay? Then there's a second meaning of intelligence, which is a little bit like, well, actually, it is taken directly from what's called military intelligence. Intelligence in this case means data, information that is very critical to your mission, that's very hard to obtain. So you kind of like, you have to invest in a lot of effort to get this kind of insight. Okay, and that's what military intelligence is. Okay, you embed a spy in a foreign country for 10 years because you want to get some insight, some understanding in the other country that you're spying on, right? And that information is precious, it's powerful, it's costly, it's very costly, right? And the modern use of that word you see in what's called business intelligence. So if you're talking about business intelligence analytics, this is about extracting difficult, powerful information set from quote unquote your enemy. Except in business, you don't have enemies, you have counterpart. And what are your counterpart? Many. In a business, the first counterpart is your client. Another counterpart you might not think of is actually your employee, right? If you think of a corporation, understanding how happy your employee are, how engaged they are, right? That is also an intelligence. So counterpart doesn't mean adversarial. It doesn't mean enemy in the sense of a military intelligence, right? So it's an intelligence into not you, intelligence into your counterpart. If you are a seller, the intelligence is to the buyer. If you are a creator, you are maybe your influencer, whatever, then your counterpart, you want to get intelligence on your influencee or your clients. If you are a corporate HR, you want to get intelligence on happy or how unhappy your employee is, your human resource, right? So that's the clandestine, covert information that's difficult, precious, costly, but powerful, okay? Finally, there is the intelligent that you would say, oh, that's intelligent solution, meaning it's clever. Okay, it's optimal solution. And this is the meaning of intelligence that AI has morphed into. Okay, so whereas I would, strictly speaking, I would call this computational intelligence. In other words, getting better, more optimal solution because you have ability to utilize, right? And expedite computational platform, very powerful computational platform. You and I are very good in 2 dimensions. We're actually better than computers. In 3 dimensions, well, we probably about the same. But in 10 dimensions, we definitely lose out to computers, okay? We can't spot pattern in 10 dimensions. We can't even spot pattern in 4 dimensions, 5 dimensions, but computer can do it just as easily. Okay. Conversely, in 2 dimensions, you can probably spot pattern much quicker than a computer. Right. So now we're talking about, and notice this little red link here. Okay. When we talk about applied digital intelligence, we are referring, okay, to mostly computational intelligence. In other words, you want your study to give you the power to actually come up with intelligent solution. Again, remember we have 4 tags in BAScii, right? So this is sort of like solution looking for problem. You don't want silly solution. You want intelligent solution, right? And that's why I told you that if you're interested in, say, sustainability problem. You can do it two ways. You can study sustainability and maybe apply some of applied digital intelligence as solution, or you can study apply digital intelligence as solution and then look to apply it to sustainability challenge. Okay. Now, technically speaking, computational intelligence, which is what I did my PhD in, sort of like an intersection of three areas. Okay. One area is intelligence because, you don't want to replicate a 3-year-old, right? But if you can get the mechanism of a 3-year-old, right, and sort of like turbocharge it with the computer RAM and gigabytes of memory, it's not going to be a 3-year-old anymore. But the first job is somehow you have to mimic or emulate how a biological brain works. Okay, so that's the first track of computational intelligence research. So that's in the 80s, this were called they were not called deep learning back then. I'll tell you why later. It's called artificial neural network. Okay, your neural cell in your brain, that's a neuron. Your neuron is not lined up in a row. Well, some of them are along your spine, but in a way, it's more like a network. So your brain is a biological network. So a computer simulation or mimicry of that is called artificial neural network, or neural network for short. Okay. Second track of that is nature's inspired solution algorithm. This is sort of like related to, well, how bees can find its way around, how somehow water knows how to expedite its flow so that it's sort of like achieve the fastest bend or something. Well, even in your blood cell, actually, there have actually been fluid dynamic studies that mimics what happened in the design of your blood vessel. It turns out that your blood vessel is very optimal in terms of facilitating flow. It's like nature has solved partial differential equation with massive supercomputer. Okay, of course, nature didn't do that. Nature just evolved. Well, if nature spent millions of years evolving all this biological function within us, as well as a society, say a social animal like bees and monkeys and apes and so forth, we can turn around and we can mimic nature's solution. Now, recently there have been physical mimicry, for example, mimicking gecko's web, right? So you can get robots that climb wall. Well, we are talking about mimicry in terms of organizing solution. Okay, so it's about solution discovery. It's about trying to find the best point in a space that's very big. Okay, how do you find the highest mountain in a forest? But you can only do it by looking 2 meters at a time. How do you do that? Well, you can think of a big swarm of bees or big swarm of birds that just sort of like spread out so that you're not just searching small area. And the bees come back and, okay, the bees not trying to find the mountain, the bees trying to find, say, nectar, right? The bees found nectar, come back, do a little bees dance, indicating the direction and the distance of the flower field, in the parlance of what we talked about yesterday, the magnitude and the direction. So the bees, when it's dancing, it's making a figure of 8, right? The way it's making figure of 8 is giving the direction, and how long it dances gives the measure of distance. So it's giving a vector. Okay, so bees are communicating vectors, but the reason they do that is because one bee has found really, really nice field of flowers. Okay, now it's not by chance. Well, it is by chance, but it's also by design, because you just spread the bees everywhere and then one found it. It's a little bit like that. So instead of getting a computer to just trying to find one solution at a time, how about let the computer separate itself into mini bees and try to find a solution and come back and report. Okay, and that, by the way, is a basis that inspires ultimately all the way to quantum computing. We'll talk about it a little bit today. Finally, it's about intelligence. Well, intelligence is no good if it's for the world of robots. It has to be for the world of humans. And it, in a way, you hope that machine learns how to build intelligence from the human model. But at the same time, you want the existence of machine to make human being do things more intelligently. So somehow man and machine has to be interoperable, able to interoperate. Okay, and that's when you get studies like a fuzzy system. We might talk about it. We'll talk about cybernetics, man-machine interface. In a more physical sense, you can think of study of ergonomics, right? That's your interface, your physical interface between you and your chair and your car. That's ergonomics. Well, in this case, it's the interface between you and data. It's the interface between you and optimization problem. Okay. So that's what we focus on. So a lot of time we get a lot of inspiration from the first meaning of intelligence and also the clever solution. That's why I have this red link here. Okay. Right. I'm just going to go over quickly. My own thesis is actually algorithmic trading. Okay. Back then we didn't call it algorithmic trading. We call it model trading. Okay. And what I did was a little bit like a bee. Okay, if you have somebody who's very good at buying low and selling high, that's a good trader, right? Well, it's hard to develop a good trader. It's a little bit of hit and miss. So in a way, I created a population of artificial traders and have them compete. And those that succeed, so they like live on and generate clone or babies, you know, so good traders get married and have baby, good traders, that sort of thing. So that was actually my PhD thesis. Of course, back then we had to program a lot of things by scratch. This was done in C++, so it's not, you know, it's not as a high level or friendly as Mathematica that you guys were learning yesterday. Literally, I have to say, you know, spell out, draw a little green square from this pixel and so forth. It's quite funny. Okay. And this is another thing. This, don't worry about the detail, but essentially it's an optimization of portfolio. Like if you talk to your parents have some money, they're not going to put it in one stock. They're going to put it in a basket of stock, something like that. That's called a portfolio. So you put some money in gold, you put some money in this stock and that stock, in this fund, in that fund, in fixed income, in government bond, and so forth. Well, this is about optimization using a fuzzy set. So again, this is about trying to find better solution, more intelligent solution that suits human being. It's working for us. It's working for us. Okay. I'm going to skip this as just screenshots. Okay. Now, this is where we start to move to, again, the inspiration. We talk about AI to machine learning, right? But when we focus about computational intelligence, getting better solution, it's still something that motivates machine learning. Now, to think about machine learning, it's best to think of yourself when you were young. Okay, when you were young, when you were a baby. Okay, before you even understood human language, you could not be taught right from wrong, bananas from apples, but you were already able to free associate. Right, you associated the scent of your mom, right? The sight of your mom with being fed, right? You sort of like organize things together. Like your dad comes with your mom, whereas your dog comes with a neighbor or something like that. So this is kind of like, nobody's telling you to organize reality, but immediately you were already matching things. You were grouping things together. Well, this thing, algorithmically speaking, becomes what's called unsupervised learning paradigm. So that's one. So there's a huge area in machine learning, in modern data science, that's devoted to unsupervised learning. It's like, give me a set of data. Don't tell me anything. I'll try to make sense of it. That's unsupervised, right? Because, you know, you leave the baby in the crib unsupervised and it's looking around and, you know, making association and so forth. Well, as you started to understand human language, then your moms come in and say, well, this is a banana, this is an apple, right? But that's not how you learn. That's not just how you learn. How you learn is when you start to try to say, mama, banana, apple, right? And if you made the wrong call, What does your mom tell you? No, 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 no. This is not banana. This is apple. Or you point to apple and you say monkey. You say, no, 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 this is not monkey. This is apple, right? So this is what's called a supervised learning mode. There is the right answer and there's a wrong answer, and you get immediate feedback. The key word is immediate feedback. In mathematics, the feedback comes in the term of the error function. Okay. And in the pre-course, we'll learn, about the meaning of calculus and what it means. Well, calculus is sort of like a rate of change of something. What happened is, in this case, you want to change your internal map to the direction that correctly identifies banana as banana, apples as apples. Okay, so there's like a slope in there somewhere that you're kind of moving along. Okay, so that's where calculus comes in. Okay, that's where calculus comes in. Right. So that's sort of like data set. Usually you will see what's called label data. Y is the label. So what's input? Input is a picture. What's a label? Cat. Input is another picture. What's a label? Dog. Input is another picture. And what's a label? Happy cat, right? And you try to get the computer to say the right thing. And if the computer sees a picture of cat and say dog, you say, no, 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 no. Okay, so you give the computer immediate feedback. So in the machine learning loop, it's doing what your mom were doing to you when you were babies. No, this is a cat, this is a dog, this is apple, this is bananas. And of course, it's only a short step in terms of a concept, to think of identifying picture to bananas to identifying X to Y as a mathematical function of X, right? To you, this one is more complicated, right? You see picture and you say, that's a cat, that's a dog, that's easy, right? But to see an X and some function and to compute Y, that's difficult. But in machine learning, it's actually the opposite. It learns X to Y first, and picture to cats becomes a little bit more advanced from a machine perspective. Finally, there's this kind of teaching where you get feedback, but you don't get immediate feedback. You get long-term feedback. Let's say you were not a nice kid, you were a nasty kid. You like to sort of like pick on your brother or sister, right? Well, if you're not nice to your friends, your mom is not there to say, no, 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 yes, 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 all the time. But you will notice that if you're not nice, nobody likes you, right? If you come to class, you come late all the time, your friend has to wait. Your friend who's here on time has to wait for you because you're late, right? Now, if the minute you come in late, I say, that's bad. That's called supervised learning, right? If I don't, I just ignore you. Come in whenever you like. But people who come in late disturb people who already came on time. Over time, you're not going to be very popular, okay? You're just going to be annoying, okay? This kind of long-term feedback teaches you that, hey, you know what? It's good to be respectful. It's better to be nice. It's better to be punctual. It's better to be on time. It's better to keep quiet while the lecture is going on and not disturb your friends, right? This is kind of like reinforced behavior, okay? The reinforced behavior is not a direct feedback. No, don't do this, don't do that. But over time, you realize you become less and less popular the nastier you are, right? Machine can also do that. We can build in a reward function. So it's sort of like a calculus slope, so to speak, so that if the machine tends to get the right answer, it gets rewarded. And this is something that you guys are probably familiar with in terms of thinking, and that is playing games, right? When you teach a computer to play games, you do that. You can't say, to play Mario Brothers, or I don't know what you play these days, okay? The right answer is to go right or left. No, the right answer is to have the ability to go right and left appropriately, okay? And over time, this gets enforced. So this kind of machine learning, you hear about AlphaGo and all that, but that's kind of reinforcement learning, okay? Learn that, yeah, over time, this is good, over time, this is bad, and so forth, okay? So simulated environment and response function is the key. So a big chunk, well, I'll give you an example. This is sort of like a machine learning and unsupervised, you see? And obviously, human eye in 2 dimensions, you can do this, right? This screen kind of looks different from yellow and blah, blah, blah. And you can notice that there are different ways of partitioning data set, right? Well, the idea is to do something like this in 11 dimension. And this is kind of what our typical supervised learning. This is a neural network. What happens? You have input here, right? You have input here. You go all the way to the output. And the output, say something like it's a vertical line, it's a horizontal line. If you get it right, it's good. If you get it wrong, then there's a function that builds a little bit of a slope for you to slide. So that's where calculus comes in. So you actually use calculus backward this way. This is the fuzzy. Well, this is very interesting. Your neuron works like this. Okay. Now it looks a little bit silly. Okay. But this is a function of X and Y. Okay. Well, you can think of your neuron as having as many X and Y as there are preceding neurons. So if this particular neuron takes input from 50 other neurons, then it's not 2-dimensional, it's 50-dimensional. So all I'm doing is a 2-dimensional analogy of what the neuron does. But notice how powerful it is. If you just have 2 neurons, okay, one saying positive for this area of the space, one saying negative or 0, okay? And you have another neuron that's sort of like saying different information. Say, I like to be on this side. So if you think about it, say one neuron, I want to be in the northeast. Another neuron say, I want to be in the northwest. Well, together, what they mean is that it's really good to be in the north. It's a little bit okay to be in the east, a little bit okay in the west. It's not good to go south, right? Because the northeast and northwest kind of reinforce each other, okay? So immediately with just 2 neurons, it's giving this complexity. Well, because of this ability of your modern machine, you have computers that have 1 million neurons, okay? And the 1 million neuron is stacked so deep. Now they call it deep learning. The word deep comes from literally that. How many stacks of neurons are feeding off each other? 10, 20, right? And each layers. So now you have millions of neurons, which is huge, okay? But it's not comparable to billion in your brain. Okay, so it's not quite there yet, but close. Getting closer, not close, getting closer. Right. So this ultimately, believe it or not, it's based on this simple building block that a computer can identify cats and mouse, or cats and dogs, and happy cat and unhappy cat. Why? Well, your brain is a little bit like this. Your brain is not complicated. Your brain is just massive. Okay, just billions of neurons, each of them very simple. And in fact, your neuron is no more complicated, no more sophisticated than frogs. You just have more of them and you have more layers. I'm not going to go into this, but you can see that, this is just as you have 2 neurons that can identify north from south, you can actually draw a circle. You can do all kinds of stuff. You can draw a funny shape, okay? Now, this is how you you can imagine that this is a representation. Blue corresponds to cat, red or orange corresponds to dog, except it doesn't happen in 2 dimensions. It happens in thousands dimension. Okay. So that's what sort of machine learning does. And we have this thing called confusion matrix. And there's a nice joke about false positive and false negative, right? A true positive is when you tell a pregnant woman she's pregnant, right? A true negative is when you see somebody who's not pregnant. Obviously, a guy is not pregnant, right? A false negative is when somebody's pregnant and you say she's not pregnant. A false positive is when someone's not pregnant, you say he's pregnant. For example, in this case, a guy, you say, "Oh, you're pregnant." So that's so this is what's called confusion matrix. It's again, think back to your supervised learning, right? Right? You can see banana and say banana. That's true positive. And conversely, you can see banana and say not apple, right? That's true negative, that sort of thing. Okay. I'm going to skip over this again. So Skip over this. Now, I just want to show you how easy nowadays. You know, I show you that screenshot of a C++, right? Back then, if I wanted to build a neural network, I have to create neuron from scratch in my C++ program as an array, build in some kind of derivative function as a numerical differentiation and so forth. Nowadays, a lot of this is built in. So this is actually an excerpt from Mathematica. So my predictor, I just give it this data, something like this. Say, this is a shirt, this is a whatever. And I just ask the computer with this one line and say, build my classifier is equal to classify and give it the data. So I'm not saying that you're going to get the best model, but in Mathematica, you know, as opposed to Python or something that takes whatever, many lines of code, you can literally say, this is my data. Build me a model that classify, you know, t-shirt from purse, from pants or shoes. Okay, just give it an example. It's that simple because it's built on years and years and years of abstraction upon abstraction. Okay, so if you don't want this kind, you want build other thing. You know, there are many kind of things. So I'm just gonna skip over this to save time. Right. Finally, the thing that is new these days that we didn't have when I was your age. Actually, when I was your age, we had the mathematics of this, but we didn't have the computational power because it requires a lot of parallel multiplication, a lot of matrix multiplication. And computers back then were doing, you know, a single multiplication at a time. A good thing is the game card. The very game card that NVIDIA makes for you guys to play 3D games, okay? I told you yesterday during class that a 3D games has a lot of 3D manipulation. And every time you manipulate, you move a point in 3D space, you're multiplying a 3D coordinate with a 3x3 matrix. Well, you can imagine the picture is a whole bunch of coordinates and you have to multiply it every millisecond or something, okay? So anyway, GPU or game card was built specifically for that. Well, it turns out this kind of massive parallel or sort of like parallelized multiplication is perfectly suitable for building neural network. And that's why you have a deep neural network, okay? Still, the first breakthrough, you know, took hours. And right now it's probably take order of minutes or seconds. Okay. The convolutional part just comes in from the fact that there's this thing called convolutional filter. Basically, it's sort of like a scanner that looks at different places in the screen and builds some kind of extraction. Like, oh, there should be a vertical line here, or there's a curve here. There's a diagonal line here, sort of scan that, you know, from all over the place, coming up all those information. So it's a little bit like filter. You can think of it as a digital filter, but it's a digital filter that computers build by learning. So it learns how to build a good filter. So that's, again, and this is easy to build in Mathematica. Okay, so go ahead. So we talk about intelligence. We talk about the real meaning of intelligence that we're in pursuit here, which is computational intelligence, right? And then we focus on the key sort of like linchpin, which is machine learning. Because before you get to machine intelligence, machine has to acquire intelligence. You can't encode intelligence. You can only give data or experience to computer along with an algorithm to learn from data. Right? So to endow machine with intelligence, you endow it with two things. One, ability to learn from data. Two, lots of data, right? Put them together, two and two together, then you get intelligent behavior, okay? Good thing is, if it can perform as good as a 3-year-old, but it's not limited to the memory or the dimensionality of the 3-year-old, because 3-year-old has only been experienced one reality, 3 dimension. 3-year-old was not born in 20 dimension. Okay. Now you mimic a 3-year-old's ability to perform really well in 3 dimension, but being a computer, you might as well give it 20-dimension problem to deal with. And it can do that just as easily, okay? So it's not initially more intelligent than us, but it's scalable in scope, right? It can do high dimension. It can do lots of computation. Now let's go to the digital part. Okay, what do you mean by digital? Well, what we mean here is actually digital economy. Okay, digital economy. And what do I mean by economy? There are actually three things that form digital economy: digital platform, digital information, and digital devices. Okay, now these are the three things that you can expect to pursue as part of applied digital intelligence. Some of this will be beyond my own expertise. So you might actually have to cross-register with, say, Department of Computing, okay? If you so wish, okay? Some of it, you know, could be some device that we have a sort of like a small scale experiment with, you know, IoT device. You can play with Arduinos or something in the lab or something like that. But if you're talking about a very advanced device, well, we don't have it in BAScii. One of the devices we don't have is satellite imaging capability. We don't have that within BAScii, right? But who does? NASA. But NASA is so nice that the Earth observatory data that they did, okay, is shared. So from your point of view, you don't have to study that digital device or the image capture from NASA. It becomes digital information, right? So nice. So nice of NASA to do that, because we don't have that, right? Same thing with medical imaging data. Sometimes you might be able to sort of like work with Chulalongkorn's medical school, right? Perhaps you can think of getting some data from them. Okay, I'm thinking along that line as well, right? And of course, all this information, it's a little bit hard to acquire information. But if you have a platform of interaction, data storage is automatic. Think of it this way. We are recording the Zoom session here right now, right? In the old days, what it means is that I have a presentation, I speak on a microphone, somebody set up a camera, takes a picture, right? Takes a video picture, takes an audio recording. But because I'm actually doing this on Zoom, all I have to do is click a little option that says record, okay? So it becomes automatic. It's that kind of convenience. Okay, so platform, information, device, you think of them, they're not separate. They're kind of like very interconnected. Okay, platform is not possible without device, right? One of the digital platform, one of the electronic platform that you grew up with is automatic teller machine, ATM. Back then we didn't have that. Now you can go anywhere and get some cash, right? Because wherever you go in the kingdom of Thailand, there's a machine that knows how much money you have in the bank, and it's able to give you a Thai baht bill to the amount that you can draw, right? Anyway, okay. So let's talk about platform. Well, one of the most interesting platform is the platform that's enabled by what's called Bitcoin. Now, for those of you who took or will take my emerging technology class, you learn about this thing where some of the most beautiful innovation gets bastardized. You know, it gets misused. It becomes something that not only is it less than original potential, it's worse. Things happen a lot of times. You do that in innovation, and that happens because of market force, social process, sort of like trends, and sometimes it takes in the wrong direction. But anyway, take my word for it. Bitcoin is one of the most beautiful mathematical construction I've ever seen in my lifetime. Okay, but now it's become nothing more than gambling platform. No different from, you know, betting on Premier League football or something like that. Okay, so that's terrible. You know what? Originally, you know, with Bitcoin, the promise was that because it was decoupled from monetary manipulation, let's say by Bank of England or Federal Reserve, it's supposed to be more stable. Guess what happened? It's more unstable than S&P 500. Okay, there's a reason for it. There are good reason, there are bad reason why we get to Bitcoin of today. But anyway, the underlying platform is brilliant. Okay, and that's the technology of blockchain. I'm not going to talk about that, but it's built on mathematics of cryptography. That's also another important thing that you have. There's public key. There's a you know, this is actually built in Mathematica, by the way. This is to show you how easy it is. I actually built this little apps in Mathematica to show what's called a Diffie-Hellman key exchange. This is like if you want to exchange private information, right? You can do two things: public key. That means nobody has a key, everybody has a lock. So you can lock something and send it to me. It's kind of like asymmetric. But you can also have like a symmetric information exchange. That's quicker, more efficient. So you have my key, I have your key. The point is, for that to be secure, I have to meet you in a parking lot and exchange a key, right? So how do I do this? Well, Diffie-Hellman is a little bit like that. You use asymmetric protocol in the beginning, but once you have the key, then everybody do it. But the point is, you can't hack each other either. Okay, you just have a key that works for the job, but you can't hack each other for other jobs. Good. So this is our so platform. I'm not going to talk more about that. Okay. I'm not really a blockchain kind of guy, by the way. Okay, I love it. I think it's a beautiful mathematical construction. But to study blockchain, computationally, you have to be pretty good with programming. Mathematically, you also have to be pretty good with cryptography. Cryptography is like a mathematics that go out of number theory. Okay, information. Well, don't need to tell you about that. Digital, well, data and information. When I was your age, it was a very clear cut what's data, what's information. Data is something raw. You write in a spreadsheet or you copy in a piece of paper. Once you process it, it becomes information. Nowadays, it's a little bit hard to say. So I'm just going to say digital information. Okay, big data. This is interesting. This is something we did for fun, basically, right? This is a map between actors and movies. So you can see something like here. This is a movie called Toy Story. Toy Story has this guy. I don't know who that is. This is Tim Allen, and this is Tom Hanks, right? And Tom Hanks also stars in other movies. So this is a fun game. This is a parlor game. You can link, okay? You can link Tim Allen and Tom Hanks by one movie. But you can imagine that Tom Hanks acts in this movie, which is acted on by this guy, which is an actor in this movie, and this movie is also acted by that guy. So it's sort of like twice as many hops to get from Tom Hanks to, you know, the point is you can actually link Tom Hanks to Bruce Lee in 6 Connection, I think. So it's more interconnected than you think, right? You think that Thai cinema is terrible because you always get the same heroes and same villains and so forth. It's a little bit not as bad, but same with Hollywood, right? Well, it turns out that everybody's linked. Everybody's kind of like joined together, and this is a big network. This is a network of 1,321 nodes. Nodes could be actor or movies, right? And so if I put actors on one side, 144 actors and 1,177 movie on the other side, these are the links, okay? So for example, you know, you have movies, Unlawful Entry, Art of War, Grumpy Old Men, and so forth, okay? So these are the links. Well, this is digital information, okay? It's collected, it's in IMDb database, right? The point is, I can make analysis of this. I can make analysis of this. Yesterday, I mentioned the word eigenvector. Well, what I did was I performed eigenvector centrality on this guy, okay? And I determined who is the most important actor in Hollywood, okay? It's this person right here. Actually, it's really surprising. It's not a smooth graph like this. Okay, in some other metrics, it is like that. But for eigenvector centrality, this guy is the most, let's say, promiscuous. He's like in every movie. It's not that he's in every movie, but he's in the movie that's jointly acted by a lot of other actors who in turns are jointly acting in other movies, right? So this guy is the most eigenvector central actor in Hollywood. Okay, do you know who that is? Okay, I'll tell you later. Okay, so let's move on to digital device. Move on digital device. Well, this is where, I just want to show you, this is a little bit old because, when I made this slide, probably screen capture, this was a fairly new thing, where you can wear something on your wrist that links to the satellite. This was my paramotoring session, right? So while I'm doing this is well, it's only 2D because it's a mapping, right? But I happen to use it while I'm paramotoring. So this is me. I start here. I make a little thing and I do a little aid before I land. Okay. So this is recorded as I am in the air. Okay. Likewise, I swam from Got Samet to Ban Pe. Right. So this is and because I was not a good swimmer. Okay, a good swimmer would be able to sight and swim straight. I was terrible. I just swim in very long time. So I ended up taking this kind of silly S curve. Okay, it took me 4 hours to swim that far. Okay, most people, the competitor on that day probably finished in 2 and a bit. Anyway, I was a terrible swimmer. But this was recorded. If I remember correctly, I put Garmin. Back then, Garmin cannot detect GPS in a swimming mode. So I actually hide my watch, my Garmin watch, inside my swimming cap so that it would stay above water. Right? I think that's how I did it for this graph. But nowadays, I can just wear it on my wrist. Nowadays, I can just wear it on my wrist, and it actually measures the heart rate. Okay. Likewise, this is a digital device. Now, what's amazing about this? Okay, this is not that amazing. So this is during a 35 kilometers run. Okay, it tells me how fast I'm going. That's easy, right? That's satellite. But here's an intelligent part. Look at this. Cadence. How does it know cadence? It knows cadence because it has accelerometer within it. So it knows when I'm hitting the ground. Okay? And if it's more clever than that, it knows by modeling movement. I tell the watch, I'm wearing my watch on, say, my right hand. So it knows that when I'm doing this, I'm putting my right foot forward. So it actually measured the balance between my right foot and my left foot. It can do that. So this is combining local processing power. This is, basically the birth of IoT kind of thing. Okay. Usually you think of IoT as just sensor, right? Some camera, something that does this, does that. But actually it does computation. Okay, it does computation. Now, in theory, it could just send information to cloud and have it processed. But a lot of time, it's literally processing here. It's calculating my stride length because it knows I'm taking the right foot, I'm taking the left foot, and I'm jumping. So I know sometimes, you have imbalance. You step longer on the right foot, or your right foot is longer than your left. It can calculate that. It's pretty amazing. Pretty amazing. Okay, so now, finally, quantum computing. I'm not even going to talk about it today, but I gave a talk on it in 2018, I think. Yeah, 2018. It's very intelligent. It's the future. It's the future. It's going to disrupt every technology. And you know what's so nice? I was saying NASA is very nice to share the data. IBM is so nice. It actually shares quantum computing time. This was when I was at SCB. I literally ran quantum computing experiment on my computer. I sent I didn't do it like that. I sent the instruction to IBM portal. IBM takes me in the queue, run it on actual quantum computer. Okay, and then gave me the result later. Okay, the result was I wanted this number 4. So it gave it probabilistically. So probabilistically, it gave this. So that's the right answer, right? If you take the maximum likelihood or the highest probability, this is my answer. So it's giving the right answer. And this is the programming step. quantum. And this was 2018. Back then, I think IBM only allowed us to play with their 5-qubit machine. I think they have bigger one now that they let the public play with. I haven't kept up with the technology very much in this space. Okay, so you know about intelligence, right? Intelligence, and essentially we don't want to just mimic human being. By the way, I forgot to tell you this. Chatbot is an example of AI in the first meaning. It mimics human being. A chatbot doesn't have to give you intelligent solution, right? So if you have a chatbot, you ask for investment advice, it may give you something stupid. But as long as you think, or you are nearly convinced that you're talking to a human being, that's a perfect AI. Okay. So as long as you're chatting, you say, oh, what should I invest in today? You know, the market is down. What do you think? Oh, well, I can suggest this. Well, you know, is it raining over there? Oh, yeah, this is raining. Okay, well, over here it's not raining. Well, I have this much money. What should I do? And it tells you to buy Bitcoin or something. Okay, so it's a stupid solution, but it is speaking like a human being. Okay, so that's called passing the Turing test. Anyway, so why do we have this? We have capability of mimicking human and therefore surpassing capacity of human intelligence. So it's human-like in form, but machine-like in scale. That's the essence of it, okay? You do it on data, but that data is so powerful precisely because it has a lot of, the algorithm is powerful precisely because it has a lot of data. Why does it have a lot of data? Because in the modern world, you generate so much data. Just by running, I'm generating megabytes of data. Okay, so data is continuously, you are generating digital trails right now. Okay, why do you think that Google Map knows where the traffic is? Because everybody turns on Google Map, and you know, a few minutes later, that machine that still turns on Google Map only moved 5 feet. So that means the traffic is pretty slow. It's a very reasonable assumption to say. So it knows real time. It's not just it's clever. We are making it clever. We are helping it clever. Okay, and that's the precautionary tale of your generation, by the way, that you are not the consumer. You are the product, because whenever you play with whatever TikTok, Facebook, you are populating that database, and they're selling that database to commercial entities. Okay, so this is the difference between your generation and mine. My generation, we were the consumer. Your generation, you are the product. But it's not a product to you, it's a product to enterprise that then sells to you in something else, okay, and makes money. Anyway, point is, now let's talk about how can we apply it. Well, I'm just gonna say it can be applied anywhere, okay? And we can go as long, as short as we like in this section. What I'm gonna do is I'm just gonna do screenshot. So sustainability, solution, health science, and smart city, okay? So these are sort of like the 3-track, okay? So we can think about agro industry. You can use AI to do, say, crop yield prediction using deep neural network, right? You can country level soybean yield prediction using deep CNN LSTM model, okay? So these are real paper. They use Earth Observatory data, like from NASA or whatever. See, you can see this. You can actually overlay geographic location with humidity, drought information. So this is called crop yield prediction. A lot of papers is done, I guess, with American-based data, because you know they have lots of money to do that. So this would be like, you know, wheat or corn prediction kind of thing. You can also predict disease and so forth. Bioinformatics. Early in the, this is a bit silly. This is kind of outdated now. COVID come in wave, right? But each individual wave is actually well-defined mathematically. So I actually create a Mathematica apps for predicting COVID, okay? And actually it was very accurate, you know, for the first wave, okay? So it got the first wave for Thailand really accurate, right? And then after a while, for other countries like United States, it's no longer accurate because they got second wave. And I was kind of like having a giggles, you know, it's, oh yeah, you know, Thailand's predictable because we are behaving well. Then we got second wave. So now nobody is predictable. Okay. You can still predict it, but then you have to recalibrate. So I didn't bother. So that's bioinformatics, thinking about information about health. There's nothing more important about health than pandemic data right now, possibly, right? So you can go to my YouTube and search for my name and COVID analytics, and it will come up to this thing, okay? And it will show, you know, the early phase, the one wave fitting, right? So let's go to something else, computational biology, right? Well, this is good. This is sort of like using computer to discover drugs, okay? Using computer to help find vaccine. Now, this is really amazing. This is amazing. A lot of biological science, you understand the chemistry, you know the link, you know how chemicals bind together, you know the human sequence. But here's a trick, right? Think of human genome as telling the instruction to print a sequence of protein. Now think of protein as sequence of beads on a string, okay? Except it's not a string, it is an elastic string. It's a stretchy elastic string, okay? And each bead has its own attractive force, like magnets. Some big magnets, some small magnets, some attract to this, some not. It's not magnet, it's actually chemical bonding, okay? You sort of like thread them in a string, okay? Stretch it and you drop, boing, it's gonna curl up. Exactly how it curls up tells you what that molecule does. If it curls up to be the shape of a pincer, it's gonna do pinching. If it curls up into a chopping knife-like shape, it's gonna do cutting, right? If it curls up and maybe form a little basket, it's gonna be able to hold things. Hemoglobin, for example, carrying oxygen, it's a little bit like that. Just a few molecules that add together and looks like a perfect basket, a basket for keeping oxygen in it and just carry it, okay? So the point is, we know from chemistry what the bond is. We know from Human Genome Project how to, you know, do sort of like a mapping and all that. What we don't know is once we get the sequence and we let go, boing, what shape it's gonna take in. And that is where computer comes in, okay? You can do computer to search combination. We've tried that. Well, the last thing what they did was they let the computer learn from a few, boing, 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 not a few, quite a lot. And then try to predict, what if I give you a different sequence? Boing, what's going to happen? What is the shape? It's that kind of learning, okay? So it's very high dimensional logic, high dimensional inference, okay? It's a bit like intuition of a baby, but massively scaled up to high dimension. Okay, so that's done a lot. By the way, if you're interested in going to bioinformatics, a good language to acquire is R, because they do a lot of library in R. Just a side information. I just happen to notice that. Okay, so a lot of, okay, this is called central dogma. Yeah, this is what I'm talking about, right? You can get the string, but you can't predict how it's going to curl up. Okay. So that's a lot of this gene expression. There's a lot of very interesting problem. Okay, I'm just going to skip over them. Single RNA sequence. Yeah, this is all. Yeah, see, this is an R screen just to show you that they use a lot of R in their research. Okay, so this is some very interesting. Okay, I was kind of giving a talk like to the computational biology group, I think, so that's why I had a lot of slides. Well, this is harks back to what I was talking about earlier about the portfolio risk return. I gave this talk at PyCon Thailand 2-3 years ago, and so I did this again. It's Mathematica code. It's very short, compared to what it achieved. Okay. More recent project. This is linking. Now, instead of linking actor to actress, I'm linking different market. I'm linking Thai bond flow to Thai FX to short rate, interest rate, emerging market, Asia equity. So, okay, this I'm doing that. So this is a Coppola model. So I'm going to, and this is finally, we talk about machine learning from pattern. We talk about graph, right? Now we have machine that learns graph, right? So this was interesting, right? when I was your age, again, we talk about artificial neural network. Computers were very good at learning mathematical function. Give me X, give some complicated function and Y. And if you try a few of these, a lot of this, and show it to the computer can learn it from numbers to numbers, or from vectors to scalar. But with convolutional neural network in the 2010, it translate picture into number. Then the output translate back into cats or dog. After that, they apply this kind of thing. They embed sentences, words, vocabulary, paragraph into vector form. It's called word embedding, okay? You have to learn about it later. But the point is, now, instead of showing a picture and computer say cats or dog, you can show a paragraph and the computer can say sad story, happy story, story about a boy meets girl, or story about a boy seeing his dog die, something like that, okay? So it can actually do something like that. Well, now, instead of having words, the most recent, the most powerful is the graph. Actually show the graph and make an inference, okay? And that's the one also that helps play with innovation in molecular biology. But anyway, I'm gonna stop here and actually go to the curriculum, which I actually put here. Okay. Now, we're still working through the applied digital intelligence curriculum, but the way I design it, it's going to be like this. But I just can't say. I can say that this should be offered, but I can't say it's going to be immediately available next class, or we have somebody to teach it, or whatever. So, just as we talk about applied digital intelligence in 3 parts, I'm going to talk about courses in 3 parts. This part focus on intelligence. Okay, this part focus on intelligence. So let's go to here. Okay, so basically computational intelligence. Okay, again, go back. Now, so I'm going to separate here in 3 tracks. One is optimization. It's meaning of intelligence as coming up with solution. Okay, now optimization is not studied traditionally in AI school. It's traditionally studied in operations research. I talked to you about that. But anyway, so this optimization means intelligence means finding optimal solution. Now, the part that say intelligence means human-like and intelligence means human interoperability, that's sort of like system intelligence and intelligent design. So these are the areas. So let's, okay. So mathematical programming, don't worry about that. Nature-inspired solution, that's sort of like the bees trying to find the sweet nectar, or me trying to find the best algorithmic trading program. And here, separate into machine learning from example, supervised, unsupervised learning, artificial realism, robot, humanoid. Now, we don't focus on artificial realism that much, okay? In other words, there are literally AI schools that focus on this, on virtual reality types and humanoid robot. Maybe in the future, again, I have to do a little bit of budgeting of what we can approach first. So chances are we're going to have be a machine learning or machine learning 1 and system intelligence design and so forth, right? So that would be the design. The idea is to focus on intelligence. Okay. Now the second part is to focus on digital economy, the platform side. Okay. Obviously, one of the biggest platform, the ubiquitous internet, right? So Internet of Things is it. Okay. And then you have things like blockchain. So I think these 2, okay, even though it doesn't cover all that is digital platform, these are the keystone, okay? So basically the blockchain and IoT, we should have a course of that, okay? And then we talk about infrastructure, energy grid, GPS. Again, you yourself will have to do the multidisciplinary bit. So it may be possible that you're inspired to study digital platform, but you focus more on energy grid. Then you will be encouraged to maybe link up with engineering department, or you see what I mean. So this can happen on your own. But in terms of basic course, I have to sort of like think of streamlining, what are the basic applied digital intelligence course we should have at the minimum that we can do really well, and something that's more specialist, right? You don't want to have all the BAScii students go into energy grid, but maybe one of you, two of you would go into that. Same with GPS network. Digital information, and that's when you go to digital data science, right? Data analytics, that's a big thing, okay? Data science, business intelligence, that's kind of data analytics. That's actually the course I'm teaching on in autumn. Then digital device, there's like embedded system, that's some area in itself, semi-autonomous. A lot of this, the proof of concept relies on having mechanical or fabrication shop. So we won't be able to do that, but certainly you can link up with the engineering department. But things like elementary robotics, Arduino scale robotics is something that's certainly manageable, okay? So we should have something like this within our curricula, okay? Now, having it in our curricula might mean we have the class, we design it, but we invite somebody from robotic labs who may not even be part of the university to teach, or who may be in a university, who may be in a fintech. Finally, go to apply. And notice the apply is separated into 3 tracks. So this is how applied digital intelligence services are the 3 tracks. So there's sustainability application, there's healthcare. Now I separate healthcare into 3 things, because if you think about it, this is a ripe area that you can immediately see the big win for artificial intelligence and computational intelligence and machine learning, right? So one is bioinformatics, computational biology and medicine. That's the thing, a lot of genome work. One is healthcare. So think of data mining, but instead of trying to find the best clients to sell your product, it's trying to find about the health status of the population and how you can design the best healthcare system. Okay, and then you can have something that's AI and IoT and robotics focus specifically in medical domain. Okay, medical domain has you can have another one on military domain. It's just that the environment, the constraint, the operating environment that's required on your AI, on your IoT, on your robots are different in one versus the other, right? So in maybe some place you have something for military application. It has to be robust. It has to be okay with data loss. It has to be able to work with muddy situation. Whereas with medicine, it's different. You have to be able to work in a clean environment and not make it dirty. So it's kind of like an opposite. Likewise, these are the IoT AI tracks for smart city that you are well aware of, like, traffic signaling and so forth, right? And you can think of 2 things. One is a sensor-based type thing, right? So you're measuring the traffic's intensity, or you're trying to model the traffic. And then you can do the modeling part, which is the modeling traffic flow. So maybe you don't detect the data, you don't take the data yourself. You can use a public domain traffic flow data. There are actually traffic flow data in Thailand that you can freely subscribe or buy. And then you can build a neural network or deep learning model to predict. Now, chances are you're going to need some graph learning, because traveling is a graph, right? You go from this place to that junction. That's a node. That's a node. That's an edge. From here to there, that's another edge. So it's not a table of data. It's a graph. Okay. So traffic information, topography, what Bangkok look like. Bangkok, Krungthep, mathematically is a graph. Okay, and the flow is a dynamic flow within the graph. So that's the sort of thing that we kind of plan. So this was sort of like, if I were given a budget of 12 courses to have as a really key core area for applied digital intelligence, where's the best place to put them along this entire concept of intelligence, digital economy, and application area. Okay, and notice the application area, I'm focusing on the 3 things that are the other 3 tracks. So it doesn't mean, applied digital intelligence is, well, traditionally, we've only got 2-3 years of tradition, but traditionally it's the most popular track. But it doesn't mean that you have to be in the applied digital intelligence track to do a lot of this machine learning. If your focus is from the problem perspective, okay, let's say your focus is on the health science, you can actually be in the health science track, but apply a lot of applied digital intelligence solution, right? I mean, if you're in a health and you study, say, policy design as a solution, then obviously it would not involve applied digital intelligence a lot. But if you think about, queuing medical supplies, how can you plan even layout of a hospital beds? Okay, how can you do rotation for, how do you switch between emergency medical staff and non-emergency when it's high COVID and low COVID? How do you optimally allocate medical resource? All this can be represented mathematically. And once you get to mathematics, you have mathematical engine to analyze, right? That's the intelligent thing about it. But again, you don't have to be in the applied digital intelligence track to be using machine learning. In fact, I can bet that most of the future application in any kind of profession, you are going to be using some part of machine learning, just like you use calculator nowadays. Okay, so it used to be a calculator only belongs to engineers, right? They have like slide rule, in fact, not calculator. Okay, nobody carries slide rule, nobody calculate. Well, nobody in general carries machine learning model, right? But in the future, it will be a little bit like that. It will be a little bit like that. Okay, so again, to go back to the philosophy of BAScii or expectation, at the minimum, let's say 40%, you be educated consumer. So you know what's good about Bitcoin and what's silly about it. 30% least will be social transformer, making positive contribution to your society, given your deep understanding of technology and innovation space. 20% of you would just benefit, maybe not from your innovation, but be able to monetize it, turn it into project, turn it into fintech, turn it into a successful business model using innovation that you have. Maybe you play a part in fine tuning, but you're not really driving the innovation. And maybe 10% of you will be inspired to be in the driving seat. Maybe you study applied digital intelligence. You study as your thesis some problem that has to do with transcriptomics, which is a set of problem in molecular biology, and you get so inspired you get a master in molecular biology. Fine, you can do that. Okay, but that would be very, very elite. Quite. I don't expect that to be the majority, but certainly that can happen. That can happen. Same with computer science or mathematics. Good. So I think with that, I actually haven't been looking at my time. I hope this is we start at 9:30ish. Okay, so we don't need to spend the whole 3 hours. It's I think 2 hours is plenty. An hour and a half is plenty. So if you have questions, certainly do ask me. You can ask me now. You can ask me later. You can talk to the faculties. The most important thing, and this, I don't know if you guys do this, but I did this a lot when I was an undergraduate. I talked to my academic advisor. Okay. Here, I've been here 2 years. I haven't seen a single academic advisee come to me and ask me anything. Okay. Well, they get my signature when they want to drop out of a course. But, when I was an undergraduate, and again, I was studying, I was torn between studying philosophy, and in the end, I made double major in physics and economics, but I talked a lot to my academic advisor, the dean's office. And so I don't know if she was actually my academic advisor, but anyway, she did that. She was that to me. So find a faculty that you're comfortable talking with, okay, and do that, because again, BAScii ultimately is a platform. Knowledge is not here. Okay, to you, I may know a lot about machine learning, but you compare me to people who spend 9 to 5 the past 5 years of their lives doing nothing but machine learning research, do you think who's going to know more? Me or him? Her. Right? But I'm intelligent enough to identify which technology fits where. That's what I'm probably better than anybody. But if you happen to have a problem, let's say in bioinformatics, requires specialization in certain kind of graph theory or graph neural network, you may actually have to work with somebody from, say, a department of mathematics. Okay? The only way you can do that is you work with your academic advice. Well, you know, because right now BAScii is like a model, like Professor Warsak said, speedboat, right? So it's not like a real liberal arts college where, you know, when I was a liberal arts college university, I literally do this before the beginning, way before the beginning of next semester. I open course catalog from so many faculties. I decide what I want to take. It never occurred to me that this belongs to that faculty, this belongs to the other side of the campus. I just literally look at the catalog like I'm shopping. I'm shopping for subject. And I like this, and I see if they offer and the times come. Oh, there's no time conflict. Okay, does it require prerequisite that I don't have? Oh, no, it doesn't. Okay, fine. Okay. It's not that smooth for you guys because you still belong here. So the easiest thing is for you to select class from here that's offered here, right? But certainly there should be something, some flexibility there that we're working with, that you might be, you know, I would love for Chulalongkorn to have this kind of universal catalog, right? And then you can pick and choose. Oh, you know what? Next year I want to take logistic management optimization course with Department of Engineering or something. Okay? Or genetics from, okay? So work with your academic advisor or faculty or somebody that you can navigate around. Okay, unless you're perfectly happy with the sort of like a standard menu that we've got, that's okay as well. Okay, so that's that. I think I'm done for the day. Sorry for the hectic. Okay, this is sort of like statistical method, and I don't need to show that. Okay. Yeah, I think we are pretty good for the day. Sorry for the hectic thing in the morning, but we finally got through, and certainly we didn't need that much time. So if you have a quick question or a long question, go ahead and ask.